We seem to do a great deal of filling in of forms these days. Whenever you apply for anything, particularly anything official, from a rate rebate to a car license, there always seems to be a form for it. And you can see from the way many of them are laid out that they're not really meant for people at all. They're meant for computers. And it seems that every day we need to store more and more information about more and more things. And it's not stored on paper anymore. It's on the computer.
We have ignition of the solid rocket boosters and liftoff. Liftoff of America's space shuttle, and the space shuttle has cleared the tower.
Houston now controlling. Mission control confirms roll maneuver starting.
The launch was perfect as the Columbia completed the pitch-over maneuver and arced out across the Atlantic. The next move, 2 minutes 7 seconds in and 27 miles up, was the separation of the solid rocket boosters.
If you wanted to build yourself a space shuttle, or perhaps put solar heating in your house, this is where you'd start, probably, in a book. And how about this beauty? It's the fattest book I've ever seen. And this is just reports on computer applications in medical care, just for 1980. Well, we're all familiar with this way of storing information, or as it's known in computer jargon, data. It's been around for thousands of years, but now it's running into trouble. These books are not the sort of light reading you'd want to take away with you on holiday. For example, we've got here the Soviet Technical Physics Letter, and you can see, imagine, Dear Ivan, I want to talk to you about the effect of an external electric field on the velocity of a surface acoustic wave in a lithium niobate single crystal. Or even more exciting, and not many people really believe this, Goodbye to the Flush Toilet. This is a comparative intellectual treatise on the flush privy versus the composting toilet. Perhaps it would be useful in the Himalayas. We're in the science section of the British Library with 85,000 books. But this is only part of it. This is one of 7 such buildings around London. This library alone subscribes to 25,000 different journals and periodicals, weekly, quarterly, monthly, so that this information is growing at an incredible rate. That leaves us with 2 problems. First of all, what are we going to do with all this paper? And secondly, how to find that idea buried in all this paper that'll make me into a millionaire. Well, let's go back a little bit. What is writing all about? Well, it's putting ideas or words into symbols. Now, it just so happens that I have here with me a page from the Egyptian Book of the Dead. And these are patterns representing ideas or words. For example, very simply, the wriggly lines are representing water. This represents purity, a newly hatched chick. So what can we do to reduce the size of all this data? Well, one way is to put it onto a computer. And to do that, we have to convert the words, the characters, and the numbers into patterns that the computer itself can handle.
To the ancient Egyptians, these hieroglyphic symbols did very well as a way of representing their ideas in permanent and storable form. And we have our own equivalent in the form of the letters of the alphabet and the signs we use for numbers. They all work because our eyes are very good at recognizing shapes and patterns. But a machine needs something much, much simpler, like a punched card, for example. All the machine has to do here is use its little metal finger to track across each column and see if there's a hole or not, and if there is, where it is. You don't need modern electronic machines to do it. In fact, it's a system which has been in use for a long time, Mac. Yeah. I didn't realize how long.
Well, you don't see a lot of these around. It's an old 40-column card reader, a card sorter. It's a nice piece of antique. But the principle's the same as was used in the old census done in 1890 by the Americans. And each of these columns, in fact, stores one character, either an alphabetic character, A, B, C, or a number. And you can set up on this one column at a time to sort them out into order.
What sort of job could it do?
Well, for example, if this was a census card and column 15, the age of the child was punched in between 0 and 9. I don't suppose they put many in 0. We set this up to the appropriate column. We put the cards in. We press the button. And here we have on pocket 9 all the children who are 9 years old with all their details, their names and addresses. And the real secret is you could take all these cards again, take them out, and then reuse them again for another analysis you wanted to do.
So it's hardly surprising that this machine has been superseded, because I suppose what you really want is the information contained in the holes in the cardboard rather than having to shuffle all the bits of cardboard around, and that's where computers come in, I bet.
Well, that's exactly right. And if you look at the way it's stored on a card, we just snip off a column of information here, and you can see quite clearly the problem. There is one character.
And that's the equivalent. And in fact, you don't, the computer doesn't just see if one space has got a hole or no hole in it. It's checking for all of them, and there are many permutations, aren't there?
Well, all possible combinations. In 8 bits, it's called a byte, by 8, a byte, and
Yes.
in those 8 there are 256 possible combinations, and they would be used to represent, for example, all the alphabetics, upper and lower case, numbers 0 to 9, all the special symbols, plus, minus, left bracket, and so on and so forth.
And that's all stored in the famous revolution, the microchip, isn't it? And it's all done in a very, very small space. What is that? What's the process inside there?
Well, I like to think of it as a sort of series of pots, and some are full of electricity, and if you like, they're in 8, and some are full of electricity, some are empty. And you can read out and detect out of those 8 which is full and which are empty. And from that you know what the combination is and what character it represents to the computer.
So, given that the information can be stored, we can sort it out in any way we choose. We can display it, we can count it, and we can scan it, looking for any particular item we want, and at fantastic speed. Now, Mac has been to see how the British Library's computer index works.
And the first thing to do is to connect the library's terminal through the telephone to any one of a number of large computer databases. In this case, in another part of London. Well, I'm looking for the application of microcomputers or computers in the home. Where do you think we should start? Computers?
OK, we'll try computers first of all.
It takes no time at all for the computer to search through its entire database. But if you're not careful, you can easily end up with a lot more than you bargained for. Oh, that's a problem.
What's the number there?
48,818 references on computers. Well, that's far too many for me to read. Let's cut that down. I'm really interested in microcomputers rather than general computers. Let's see if that cuts it down at all.
Let's try the word microcomputer then.
So to cut down the numbers, you can ask it to search again and again, matching on different words. 7,559. We've got to thin that down. I'm not going to read 7,559 references. What about home? Let's try home.
Yes, we'll try... What we can do is try to select those with home where it occurs in the title. And that's how we do that.
Well, that's more likely to give us a manageable number. I've got it.
A smaller set now, 46.
We're down to 46. That looks more reasonable. Can we look at what they're about? We'll get
Yes.
some titles out anyway and see what we've got.
I'm asking the computer to type out the first 5, just as a sample.
Now we've matched on personal computers with the word home in the title. Electronics in the home, that looks good. And here are several references. Home computers, that's okay. No pet peeves, whatever that is. And the professor rests at home. Adapting a home computer for data acquisition. Well, can we have a look at a bit more detail of the of electronics in the home?
Yes, we can print out the first one with a bit more detail.
When you've finally narrowed it down, it doesn't just give you the number of books, but an abstract of the content of the book itself. The author shows how the expanding thrust of electronics is likely to penetrate and influence our home environment of the 1980s. The home of the future is likely to become a centre for incoming and outgoing electronic signals, which will be used by members of the family to meet their particular needs. Well, out of all those thousands of books, we managed to find the journal that was in.
And you got it
There
very
is.
quickly too. But why, for a job like that, do you have to use your computer to talk to another computer? Why not have all the information in a box like that?
If you take a book like this has approximately 400 words on a page.
Right.
And so if you look at the screen of this television, on you'd need 3 screens like this to be the same as one page. So that's quite small. The 32,000 characters in here is about 12 pages in this book. So when you start talking about books, that 32,000 seems relatively small.
And that's obviously why you have to extend your storage capacity by using tapes or floppy disks, that kind of system.
Yes, the tape or this small floppy, that would handle about, at its maximum packing, its maximum amount it could store, would handle about a whole volume, the characters in a whole volume.
And this is about twice the diameter.
Yes, it's about double the amount of characters. That would hold about 1.2 million characters as a maximum.
Right. And for really big storage jobs, I suppose you need those really big hard disk memory banks, is that right?
Well, this one isn't one of the biggest. It's a sort of medium-sized machine, and this disc will hold about 80 of those novels, or the characters out of 80 of those novels.
That's not just one disc, is it? There are several.
No, there are 5 discs here, and the heads go in between to read the data, which is stored magnetically on those discs. And we can load it on the machine quite simply like this, bang, bang.
Oh, and there's the magnetic surface. In fact, it looks like magnetic tape, sort of laid out in the form of a flat gramophone record, almost.
Well, it's exactly the same principle, of course, but it's obviously much faster to access it, just like a gramophone record. You can pick an individual item of data out on it.
Right. Mind your thumb. And again, the bigger the machine, the bigger the storage capacity.
Yes, this particular machine, although not a very big mainframe machine, it has in fact got 1 million bytes of storage as opposed to the 32,000 that this little micro has. But the breakthrough is going to come with, I think, this, which is the video disc. And this will store the characters on this one disc that you'd need 3,000 books to store. And another way of putting it, for example, with cassette tape, it would require enough cassette tape to stretch from London to Chicago, and it would take 4 years to read that cassette tape.
The capacity to store the equivalent of 3,000 books is like the size of an encyclopedia.
Well, you'd actually get the whole of the Encyclopedia Britannica on this disc.
Well, let's just peep into the future for a moment, and we've got a little program lined up here, which could be the Encyclopedia of the future. If I type in Space Shuttle, and there's your page of information. The book is open for you, and to make the page move so you can carry on reading it, all you have to do is press the space bar. What's more, this is something a video disc could do in the future. Not only do you have pages of written information, but if you typed in the word picture, and this is what you get. And make it move by doing that.
We have ignition of the solid rocket boosters and liftoff.
But uses like that for the video disc are still a long way in the future. Because the computer can store and manipulate such vast amounts of information, we're only now beginning to discover ways to use it. Jill Neville reports.
Thank you very much. When you're ill in hospital, you need good, wholesome food, and it's important that you have a choice. A system of menu cards has helped in many hospitals, where you mark the card with the food you want, but you still have to order up to 24 hours in advance, and by then you mightn't be feeling so good, or you might have even been discharged. And that's meant a wastage of up to 20% of the food in some hospitals. Now, I ordered my lunch this morning, and this omelette was cooked in the kitchens just 6 minutes ago. The process has, of course, been computerized.
Of course, the computer has nothing to do with the actual cooking, but it greatly speeds up the counting of the dishes on the 500 menu cards. The patients benefit, and so do the chefs, who now know the precise quantities to be cooked. The computer the catering team chose can be bought in any high street computer shop, and it's small enough to fit on an office desk.
For the operator, the system couldn't be easier to use. Getting the information into the computer is also easy. An optical card reader scans each card and detects the mark that the patient has made opposite his choice.
But the computer can do more than just gather information about the number of dishes and meals. It can help the catering manager plan and cost the menus. Or, if it's given the exact recipe of each dish, even down to the last pinch of salt, it will print out the shopping list the chef needs to take to the stores.
Dish recipe code. So let's have an MC012, which happens to be the beef goulash.
What's more, if the computer's programmed with the price of each commodity, it can combine that with the shopping list and tell the catering manager the total cost of the day's meals, or the cost per patient, or indeed the total cost of any of the ingredients used in the kitchen that week.
And on the printer, out comes an analysis of how much that dish is going to cost.
The day-to-day running of the catering office is also greatly assisted by the computer. It's available to any of the staff who need it, and the information it can give them is only limited by the ingenuity of the programs they feed it. What started as a simple aid to reading menu cards has proved to be far more valuable because of its ability to process and retrieve information.
What the computer has also proved are that soggy chips are no longer the order of the day, because we know from the printout exactly how many portions of chips are needed on each of the 30 wards. We can divide them into groups of 5 and cook the chips in batches, exactly the right amount just before they're needed. The key to the whole operation is this timetable. It's almost military in its precision, and it's adhered to rigorously. 12:58 is the time the next lot of things are due to leave for the wards.
At this hospital, they've had the computer system running for just 2 years, and it's paid for itself over and over again. It's now being installed at hospitals all over the country, and that means savings of hundreds of thousands of pounds of taxpayers' money every year.
Obviously a tremendously valuable thing for any hospital to have. But one thing I want to know about computer memory, it's you put stuff into storage and then you get stuff out. How does that really work, that business?
Well, in BASIC you have things called variables, and all that a variable really is the location in memory where your data is being stored. You don't have to know exactly whereabouts in memory it is located. The computer looks after that for you. All you have to remember is the variable that you've called it. And I think if you take a visit to memory, or in this case a bank vault, you get a rough idea of what I mean. In a bank vault, you give them your name, they may look at a list, and they'll come out with a number where your worldly wealth is located. In exactly the same sort of way, in BASIC, you give it a variable and you name it, and the computer will decide where it's to be located in memory. And whenever you give it that variable name, it goes to that location and pulls it out. It has no idea what's in there, but it just knows that when you give it that variable name, it goes to that position in store and takes the contents out, or copies of them, and gives them to you.
So just like the bank vault, the bank don't know what you've got in your box, so the computer doesn't know what's in that memory, and you don't know where the computer's located that particular bit of information until you want it, and the computer goes and finds it for you.
That's precisely correct, and like a bank, when you give your name, you always get what's in that box.
Right.
Well, we put together a little database here of 4 of your friends and their birthdays, and we're calling these variables. Name one with this curious $sign, which I hate, which says it's a string, in other words, alphabetic and numeric, but not to be calculated on. But name one, and Jane, is the contents of the memory location which the computer knows as name one. So you say name one, you're going to get Jane.
Right.
Date one is another variable name, and the contents of that location is 23rd of February, and so on down the thing, with name 2 be Mike, date 2 being the 15th of June, and so on.
Fine. The next bit I'm sure I can work out for myself. I mean, that's asking the computer, when you run the program, to write up on the screen, enter keyword. That's telling you, as the operator, to start.
Exactly.
Okay. And input item string.
Now, you remember that because then the computer comes back to you with a little question mark, which is saying it's expecting some input from you. And when you type that in, it's going to know that as item. It's going to call that piece of information item.
Okay, so it's going to be 70 next, I guess. Am I right?
70. Now, I hope you're going to be able to work this one out. Well, what you've got in there now is item. So if the item
I thought it was going to be one. It's going to be one of these, if something equals something, then something or other.
So if item dollar symbol is equal to name one.
Item string. Equals, I bet.
Equals name one.
Right. Then
we want to print her birthday.
Right.
So then print date one.
And you have to say then, because that's its language.
That's part of basic.
And print is part of its language.
Right. Date one with the dollar.
Date one, and the dollar sign means it's a string of numbers and letters, not something that's going to be calculated
Correct.
with. Right. Okay. Then print date one strings. All right.
Now, obviously, we've got to do that for everyone, the way we've written this program, for every one of the pieces of data. But we've got a little program which we've written on
Well,
cassette.
that saves a lot of time. Otherwise, it could be flogging through all
yes,
the...
we'd have to type them all in at the moment.
Right.
Now, what we're doing, in fact...
Now, load we've got
load
to do, haven't we?
dates, I've called the program, in quotation marks.
Start the tape.
Start the tape.
Press the return button. And then it's searching. Right.
What we're doing effectively is very much the same sort of thing that was happening when you typed Space Shuttle. And
Yes.
It went to seek in for the locations in Space Shuttle and bring that into the terminal. Let's just list 70 to 100 and you'll see what we've added to it. Those are the logic statements there.
Yes.
Connecting name 2. If item is name 2, then print date 2. If item is name 3, print date 3. If name 4, print date 4.
Right.
Let's see if it works.
Run. Now, I've forgotten all my friends' names that you made up.
Try Mike.
Jane was one
Jane,
of them.
that's right. 23rd of February.
Oh, we'll try another one. What was another name?
Mike,
you said?
Yes.
15th of June. Very good.
That's not bad.
Works.
But it's ended rather abruptly, of course, and you could enhance the programme by putting their addresses on or putting what you sent them last year for their birthday as a present. And it's almost limitless what you could do to this database.
That's all feasible as a natural expansion on a microcomputer like this. To have a big home database.
Totally feasible.
Right. Well, it's pretty clear then that given a few more lessons and a bit of practice, I could have access to quite a lot of stored information. But some of it could be beyond the four walls of my home computer. Out there in computer land, as we've seen, there's a vast amount of stored data, and much of it surprisingly easy to get at. Now, that accessibility is something people are beginning to worry seriously about, including journalist Rex Malik.
What we do with computers has always depended on the cost of storage. Well, the cost of storage is becoming trivial so that we can all hold almost any data we like on a computer. Does this mean that there's a kind of electronic big brother waiting out there in the future? Well, yes, I'm afraid there probably is. For the technology is now beginning to place awful temptations in front of administrators. Do it fast, do it easily, do it cheap. What we need is law, custom, and procedure. We need to be able to control what is held on computers, who has access to it, and how they can use it. And we need to be able to correct the record. What worries me is not that Big Brother will get it right, but that he'll get it wrong. The trouble is that people tend to believe what computers tell them. Well, they shouldn't. There's a more than 20-year-old rule in this game, and the sooner everybody memorizes it, the better. It's garbage in, garbage out.